Okay. So yeah, let me do a slideshow. Right. So this is week 9, and so I'm sure all of you have gone through most of the lectures till now. So this is one of the most important weeks because you have been taught attention and transformers in this week, which is kind of like a huge milestone in the history of deep learning. So Uh, and in fact, we were some of the people who actually watched this transformation. There, first initially RNNs and CNNs were there, and then yeah, and then this transformer and attention came, and it swept everything. So it has replaced everything with itself. So yeah, so that in that way, this is a very important week. So now that some of you have joined the call, so since this is, I know that this is generally the last class of the week and most of the topics are very repetitive. So that is why I wanted to ask you, like, can anybody like tell me first of all as a story, like what was the problem with RNNs? Why did we require attention at all? And what is it? What attention exactly is? What attention transformers? This concept, what it exactly is, and why transformers are used, in so much abundance these days? Can anybody unmute and tell me as a story? Because already I think you have gone through a lot of material this week. So, for example, if any of you has gone through the previous lectures also, you could just tell me, for example, like what is wrong with RNNs first. Let's begin with that. What is wrong here, and then we can go slowly towards attention. This is to make sure that you also understand what's going on. Anybody?
Sequential and things like that, it will be difficult to data.
Your voice is actually breaking.
Keep had the capacity to handle sequential data,
Hmm.
but long sentences, the words, for example, to be held on a long-term basis, and then referring to that word became an issue. That's why the transformers came into picture.
Correct. So, in other words, what is going on is something like this, that this example is actually given by everybody, and this is also very true. So, last week, actually, we learned about RNNs, and we also learned about, first of all, the problems of RNNs, like the problems of forgetting previous words that are a little bit far away from the current word. So, RNNs tend to forget that. That is first. Second is, suppose you have a this kind of a architecture, neural machine translation. So what is involved here is that there's a suppose an English sentence here, and you want to translate it to Hindi sentence. Suppose so you will have an encoder decoder like this in a normal RNN based system, where you first process the English sentence using an RNN, that, and in the final hidden state you get a kind of aggregate information of the entire sentence. You call it the context vector, and you pass it on to the decoder. Now the decoder will, now basically the decoder has what? It has the information that was the aggregate information that was there for the from the encoder, basically the description of the English sentence, and based on that you are generating the Hindi words one by one. Now the problem with this used to work very well, but one of the problems that came up is that all the context, all of the summarization that you are learning in this vector, this is first of all, this is all you know encapsulated in this one vector, which is also dependent on kind of in this way. It consists of the, it's connected to the last word in the English sentence, in the source sentence, which means it consists of the these parts, they are more present in this context vector. They are more, so the context vector thinks of them to be more important just because they are close to this context vector. So by the time this is constructed, it has forgotten a lot of these things. So it's kind of a little bit more dependent on the last words in the sentence. That is why people saw that, okay, capturing the entire information of a sentence using one context vector, which is connected to the end of the sequence in this way, is not enough. We need to do something more. So that is why the concept of attention came up. So yeah, so that is why the concept of attention came up. Similarly, in a typical image captioning network is something like this: that you have an image and you have a CNN like this, which gives you some feature vector, some feature map, and that feature map is flattened to get your context vector, and that context vector is then passed on to the decoder to basically generate the words. Again, this context vector, people have seen that this may not be always enough to describe the entire image, and just there's this one vector that is there which has to describe everything, from which you have to. So this is not a vector that can only generate your classes. This is not a vector to which you can append a fully connected network and do your classification. This vector will give you all the information necessary that is required to generate an entire sentence or an entire paragraph on this image. So you can imagine how important this vector is going to be. That is why you need a lot of information to be there inside this vector, which is actually, people have empirically seen that this kind of an encoder is not enough to create a very enriched context vector. So that is why people came up with attention. So a little bit more example, like for example, suppose here like it's seen, it's a translation from English to German, and what is shown here is that so whenever you translate an English sentence to a German sentence, it's not that word by word it will be all the positions will be maintained. So here to reach, this actually when you translate to German, this is towards the end. Okay, so that means what, if you take a diagram like this, so to reach is somewhere in the middle, whereas your this the German translation, whatever this lies right towards the end. So it has to carry this context vector, first of all has to carry the information of to reach, and then it has to pass it on towards right to the end of the decoder. So that is why, I mean, this is problematic. This is basically, we know, based on our knowledge of RNNs, we know that these are things that RNNs find to be extremely difficult. So that is why in these situations generally RNNs do not work that well, and that is why people needed something a little bit more sophisticated to work with. Right. So attention. So one thing that attention wanted to do was to, instead of, so again going back to this diagram, what does this diagram depict? That your your current word, suppose the current word is the, so it's dependent on your previous word. That word is dependent on on that previous word, and so on. Right. So that was the story of RNNs. Here what they are saying is that why not take, so suppose your current word, suppose that is xj as it's given here, it can be dependent on so many words in your this thing in your sentence, and it's not only dependent on the previous word or the next word. Okay, so why not take the entire context into consideration, and then kind of figure out, like, in the context, if there are capital T words, which of the words are more important to this to this xj, and which are less important? Why not figure that out? Why do we have to go in the sequential manner? So that is where attention came in. So what happened there is that you have these words x1, x2, xj minus 1, xj, xt. All these words are there. So basically t words 1 to t. And now what generally transformers do is, as it's written here, that uh, you want to create, so you have a representation for this word initially, but now you want to create a new representation that is not only, that not only comprises of the meaning of xj, but also of the context around it. Not in a sequential manner, but in this way. where it takes every word in its neighborhood into consideration and not just the previous word, right? So that is what people have tried to do using attention. So how is it done? So suppose you have these words and you have kind of converted them to some embedding, and what you now want to do is that given your current word, you will somehow using these embeddings using the embeddings around the in the neighborhood of the current word, you'll somehow try to understand which of the words are more important to this particular word through some similarity score. We'll talk about that later. Through some similarity score, we are trying to see which of the neighboring words are more important to this word and which are less. Based on that, we'll put for this particular index j, we'll put some scores on all the neighbors, right? That is given by this alpha t comma 1, alpha t comma 2, and so on. So here yeah, so basically, yeah, even though it's J here, the notation is a little bit confusing. I mean, we are trying to find out the representation for word with an index T, suppose. Okay, so what we are trying to do is we are trying to look at all the neighborhood of T, and first of all, and what we are trying to do is we are trying to assign scores to all the neighbors of T, right? So to the first word, we assign this alpha t comma 1, to the second word we assign alpha t comma 2, and so on. So now this, what does this alpha tell you? If the value of alpha is this, any, suppose any alpha t comma I, if that is very high, that would mean that your current word t is highly very very similar to that particular word I. And if the alpha value is low, that means that that word is not very similar to your current word with index t, right? So you figure this out, you figure this score out for every neighborhood word that is there, and then you do a weighted average of all the vectors that you see here, right? And that weighted average you combine with your current word to generate your final representation. So what that representation does finally is that gives you kind of a, like, for every word in the sequence, it's like you have a very very summarized aggregated information of the entire neighborhood inside your word vector itself, inside the new word vector itself. So that is what attention does. So as it said here, weight vector is the measure of the similarity or alignment of the state at time t with all the hidden states. So with all the hidden states, you are kind of measuring a similarity, and thereby you are generating some score for each word in the neighborhood, and then you are combining the neighborhood with respect to those scores. So your given an input word, what you do is something like this, where so CT is your final representation, and what you do is basically you suppose you have figured out the score for each each hidden embedding 8j, and now you are doing a weighted average of them and keeping them inside CT. And how you do that weighted average is generally how you find the score is basically generally in a intuitive way, you can think of this score function as a similarity function. So you're trying to find out, like, how similar are your is your current word with respect to your neighboring words, and then basically what you do is you do a softmax in order to get a probability distribution. So such that basically when you do a weighted average sort of thing, you would always want your weights to sum to 1. They should be between 0 and 1, and they should sum to 1. That is why this softmax sort of a function is used, so that your um, yeah, so that your scores are all summing up to 1, and you basically use some sort of similarity between the current word and all your neighborhoods in order to calculate the score. So yeah, I mean a similar in the spatial data. So suppose you have an image like this. The concept is very similar, that you have an image like this, you pass it through you know a CNN like this with an FC network, and you get some vector, output vector, and there is no, at this point there is no spatial information there. So what you would want is that maybe what might happen, one thing that we also mentioned while teaching CNNs is that CNNs generally look at, the local picture. So at any place in the image, any pixel in the image or any small patch in the image is kind of, it's assumed that it's kind of dependent on the neighborhood in the image, local neighborhood in the image. Whereas probably we assume that we assume that probably this part of the image is not dependent on this part. So that may not always be true, and that is where attention has come into images as well. Even though attention seems to be well aligned with text and words, it has come into images as well, where what they are saying is that you want to, so this notion of context that I talked about, that you as a word might be dependent on all your neighborhoods in some way or the other. So that is the same notion that has come up in images as well, that if you are a, suppose what you do here is, in order to do this attention, so you have a feature map like this, where of dimension m cross n cross c, where c is the number of channels. So what you want is, given this sort of a vector inside this particular this particular feature map, so this so yeah so basically what you yeah so what they're trying to say here is that you want to find out, given this particular yellow vector, what how do you measure, basically how do you uh, how do you extract all the contextual information that is there for this particular vector and embed that information into this vector. So how they do that is that they take out this vector. So they basically some unroll into this, as it's said here, they unroll into m cross n, this vectors of dimension c. Okay, and so now imagine, so this space has been divided into um, C, vectors of dimension C, and the number of such vectors are naturally m cross n. So now you have suppose picked up, this is your current vector, and what you will do is you have other m cross n minus 1 other vectors also along with this vector, along with this yellow vector, and the way that I said, in a similar fashion, you basically apply some attention on top of this yellow vector, with respect to this yellow vector, and you do a weighted sum of all its neighborhoods, and what you get is the final representation for this yellow vector, which is consisting of not only the local information as the CNNs give, but also some sort of global information where you are putting information across all these areas into this based on some attention score that the network is figuring out. So how these scores, so the fundamental most important thing in this is how do you define the scores. So all you need to do is, in order to compute attention, is to compute this score. So given your current word or current vector image, image vector, how do you how do you compute your score with respect to the neighborhoods? So that is the single most important thing in attention, because uh, the fundamental thing that you are finally doing, ending up doing, is basically doing that weighted sum. So this alpha calculation is the most, perhaps the most important thing that you need to do, um, to implement attention. So that is why this alpha calculation is done in different ways, and again it's very based on alignment scores. Sorry, my bad. So it's very based on the application that you are, developing. So one one of the easiest things to do is perhaps to use a cosine similarity. So as I said that you can think of the scores as in the sense of some sort of similarity between your current word and the your neighboring vectors. So that is the easiest thing to do would be to apply cosine similarity on in order to compute that similarity. And there are, so that is called content based attention. So all of these are basically very popular attention mechanisms. There are different types of attention. So Most popular are this content based is always obviously there. Additive is another very popularly used attention mechanism. Dot product attention is another attention mechanism. So you can see that dot product and cosine, they are not very different. More or less they are conveying the same thing. They are finding a sort of a similarity between this st and hi. So they are more very very similar, and this dot product attention is very very commonly used. And also there this attentive attention is there, where instead of just computing some, so these are all, you can see that the network has no part in it. These are all unlearnable things. All you are doing is you are measuring some sort of similarity between these two. I mean, not unlearnable, but here you are not explicitly involving any learning. But there are also, you can see in all these variants that so this I mean these scoring functions are basically, they comprise of these extra things like VA transpose, WA, and so on. So all these are learnable parameters. So while this means that while you are scoring your current word with respect to the neighbors, you are still involving some learning there. You are learning the through your neural network, you are learning how similar they are going to be. So that is why these WAVA transpose. So I'm not going to go into the details of these, but yeah, people do use them. And as I said, that additive and dot product are very very commonly used, right? Okay, so I think, yeah, so attention, yeah, so whatever I said about attention, so things will start making a little bit more sense when we go into transformers. But yeah, let's look at it from the image captioning point of view. So image captioning is a task where, so you have been, that's a very interesting task actually. It's a multimodal task. Multimodal means you have an image, you have to, your neural network. Till now, what were you doing? You were processing images alone through CNNs. You were processing text alone through RNNs. And now yeah, now you have come to know that okay, transformers are there, which can process both, right? But even then, whatever tasks we were looking at, all of them were processing the text and the images alone. So now image captioning is one task, which is very interesting. Why? Because it, uh, you know, the, now it's something very, very human like, where you will be, the model will be given an image, and the model has to, I mean, it will be given an image and it has to describe that image using some natural language, right? So now it has to be it has to deal with both the image and the text. That is why it's called multimodal. So there are other tasks like, I think you have gone through. So visual question answering is there, text to image is there, where you'll be given a piece of text, and that your model has to create a image based on that text. So all these multi, or these models are there, which can process both of these together. So what does a typical image captioning task involve? So you have an image as input, and you have to describe that image in some sense, right? So we know what. So this slide is basically based on very very traditional image captioning systems, where you have a since you have an image, you know that your images can be processed well by CNNs, and you have text, you know that text can be processed very well by RNNs, right? So why not combine these two fundamental architectures in order to compute a task like image captioning? So what used to happen before is that you give the image as input to a CNN like this. So this is a, I think, either a ResNet or VGG architecture. It's a very deep neural network. So you give the image this sort of a CNN, and that CNN supposes so it consists. It's a, because VGG, ResNet, all of them are pre-trained on ImageNet. So there, the last connections, the last layers in the CNN network are always a FC of 1,000 neurons, because there are 1,000 classes in ImageNet. So because you are doing a different task here, you just cut these off, and you take this, I mean the final, I mean the second last or third last FC layers. Okay, so you pass your image through this, You take the vector out of this. So FC4096 means that you'll get a vector of dimension 4096. And now you also have the RNN. So now what you have to do is you have to take the information of the image into account and then generate your sentence or paragraph or whatever. So that is why, and the normal RNN looks something like this, that you generally suppose if the image was not there, you were just generating the sentence. What would happen is you will start with a start token, pass it through the RNN, and then you generate the next words one after another. But here, since you need the image information, how do you insert it into the network? Just by, so the technique is very simple. What you do is you take the output from here. So you get a, basically this gives you here, this is a like a vectorized representation of your image, and you append it to this 80. 80 is your initial hidden state, right? So like initially it was something like this. Your 80 was some value something like this. Now you are adding this information. This B is basically your vector from this particular layer. So you are adding this information into the network, and you are, that is how you are telling the RNN what was the image, what was the information stored in the image, right? So, and now the RNN generates the words, it basically learns to generate the words one after the other. So this used to be one of the some of the state of the art image captioning models. But again, the same problem is there, the RNN problem that we used to face. So you are just giving the information of the image here in the initial stage, whereas you get the final stage way later somewhere. And by the time you have reached the final stage somewhere here, you have forgotten all about these things. So that problem is still persistent in this type of an architecture. So that is why people infused attention in image captioning tasks as well, right? So where your you are compulsorily forcing the model to, instead of just sending the image information to the initial first hidden layer, you send it across to all the hidden layers in some way, right? So correct. So how they do that is that, suppose you have this image like this, and you have a CNN network which gives you some feature, right? So that is represented by this small v, right? And now what will happen is you'll send this small v to some initial hidden state of the RNN, which is 80. Now this hidden state will basically, this RNN is trained to output two things. One is your obviously your next word, and second is your attention scores itself. Okay, so this 80 will output something called A1, and what you'll do is you'll just multiply this A1 with V, right? So this is kind of the weight that you want to put initially on your on this V vector. So that weight is being learned by the network itself here, right? And now what you do is you do this A1 times V, A1 multiplied by V, you get a new vector, and you are passing that to the first, basically this first word. I mean your first word is suppose Y1, and you are passing this Z1 along with Y1 to the first hidden state, where Z1 is nothing but the weighted, uh, I mean not weighted sum, but yeah, this A1 times V. Now what happens in the second stage is, so you have this Z1 and Y1, you pass it to H1, just like a normal RNN, and this state has to output two things. One is this A2, which is the weight for the next stage, and this D1. So D1 is nothing but, here in this stage you are basically predicting your uh, next word, right? So this particular thing will be kind of like a classification over your entire vocabulary, where all you have to do is do a softmax and take the most probable word. So that becomes your D1, and you train it by the cross entropy laws. Similar, but here the A2 that you got, this is now the weight, basically the underlying, I mean, what they're trying to do here is that at each stage, you're figuring out how much of this visual information is required for the individual uh, words at every stage. So some words may be very very dependent on the image. Some words may not be dependent on the image that much. They are just dependent on their previous words, right? So that is why, in order to instead of giving the entire information right at the beginning, they are basically helping the model to learn how much importance to give to this v at every stage, and they are giving it as input. Whatever importance they are calculating, they are multiplying it by v and they are giving it as input at every stage. So that is how this image captioning with attention happens. So the gist is that you, at every word in the caption that you are training, you are sending the visual information in some sense, which was not possible in the previous stage. Previously, you were just sending your visual information to the first word. Here, you are sending it to every word, and you are learning. I mean, how much importance every word has on the visual information. You are learning that as well through this A1, A2, A3, and so on. Yeah. So that is image captioning. Right. So now this is like the biggest one of the biggest things that have happened in deep learning in the recent past, and that is the advent of this architecture called transformers. So transformers are nothing but basically they are so whatever attention mechanism I showed, this entire architecture is built on top of attention, right? So and this transformer is being used in text, images, audio, and whatnot everywhere. Now you see that transformers are surpassing all the traditional architectures and they have become like the state of the art, right? And so here what has been done is, it has been, I mean, some of the important subparts of transformers have been listed: self attention, multi head attention, positional encoding, encoder decoder architecture. So yeah, briefly we'll go through all of them. um, so like for example, this is a typical encoder decoder architecture. So here you are giving, this is again some encoder decoder. One very common example is what we always show, the neural machine translation. So you have an input sentence or paragraph in some language, and you want some sentence or paragraph that is a translated version of this, translated to some other language. So basically, so like RNNs, again you have a, here also you have an encoder decoder architecture. So in transformer what happens is there's an encoder layer. Okay, so we'll go through the encoder layer in a bit, but so what happens here is that so this encoder layer on the encoder side, basically you have layers like this, layer after layer after layer, called the encoder layers basically. And from the encoder layers, whatever information that you learn, so the objective is that all these encoder layers will learn the information of this particular input language, input sentence, and based on the information learned, it will now go on decoding the language, decoding the sentence. So uh, to basically translate this input sentence to an output sentence in the desired language. So now, I mean, this particular whatever we are going to talk about in the next few minutes is basically taken from this legendary paper called Attention is All You Need. So whoever has not read it till now, I recommend that you go ahead and read it because it's very very seminal and a very very interesting paper. So you will find it surprising that okay, this is how people have solved the problem of RNNs. So it's a good read. There's also lectures by this person Vaswani on YouTube. So please go ahead and look through it because it's much better when you learn about these concepts from the man himself. So yeah. So okay, so let's, instead of going through this architecture, let us yeah, let us go through individual sections one by one. So yeah, you, these are basically some of the parts that make up the transformers. So the individual parts of the transformers are here. So let's start with something called positional encodings. So Positional encodings means what? So let's go back here a little bit. So whatever I described here, my description was something like this, that okay, your current word should not be always dependent on just the previous word or just the next word, right? Your your current word might be dependent on a number of words in the sentence that may be far behind or just just behind. You don't know what dependence this particular word has on other words in the neighborhood, right? So that is why this attention concept came into being. But in order to, so if you look at this sort of a formulation, the problem with this sort of a formulation is that you are losing the entire positional information in your sentence. So now if you compute something like this, ct equal to this weighted average of all the 8 j's, you are kind of losing what is the position of ct in the sentence, and what is the position of these 8j's also in the sentence, right? So that is also, you'll obviously understand that in language the position of the words is very very important in a sentence. So that is why this positional encoding thing has come up, this thing which will do what, that even though you are doing this sort of a weighted average of your entire neighborhood, you are still taking the position of your current word into account. So current word into account for all the words basically, right? So what you do is, when even like just like RNNs in the transformers also, you begin with a word embedding. You do not begin with the raw words but with a word embedding, and you encode the position of that word in the sentence in some way, and you basically concatenate or add that positional encoding to the wording encodings that you formed. Okay, so as it says here, it helps in maintaining the order of the words in the sequence. So how does this positional encoding happen? So right, so let me open this one. Yeah, so I think this will give a little bit more clearer. Uh, Nothing more. It's just the same thing, but all these values are defined here. So what you do here is that, suppose you have a word at some position POS, right? And what you do is, how do you calculate the positional embedding? So the positional embedding will be same as your original word embedding. Okay, so if your original word embedding is of dimension 5, your positional encoding will also be of dimension 5, right? So how they do that is that, so they do that using this sort of a sinusoidal formula, right? And so everything is defined actually here. So this I basically stands for the individual components in the vector. D stands for the entire vector dimension. Okay. So now keeping that in mind, again let's go back at our formula. So what does 2i mean? 2i means any even position in your vector. 2i plus 1 means the odd positions. Okay, and EOS means basically your word's position in the sentence. Suppose it's the fourth word or the fifth word in the sentence. So like if I say I like Bangalore, then like is the second word. So that is then this pos value will be 2 for like, for the word like. And now you have a word embedding for the for the word like. So suppose that word embedding is of size DEMB, this thing, the denominator one. And now for each position inside, for each component in that vector, word vector with the dimension DEMB, you either have odd positions or even positions. So if it's an even position, you apply this formula. If it's an odd position, you apply this formula. So if anybody asks me today why they have gone with this complicated sort of thing, I have no answer to that now because I don't remember it. But yeah, it was kind of justified in the paper. This attention is all you need paper. So why they chose this sort of a complicated way of encoding the positions instead of straightforward, saying which position, whether it's a fourth word or fifth word. Why they did that, that thing will be clearer in the paper. Correct. So now self attention. Self attention is what? Self attention is basically you. So okay. So let's try to look at it in this way. So you have an embedding x. Okay. Some input word x. Okay. And now what you do is, so attention is computed using these query keys and values. Okay. And now, so what does that mean? I mean, so yeah, what happens in the, if you want to think of it in a like a story, what will happen is, so you have these query key and value vectors. Okay. So now what you'll do is, the dot the this weighted average thing that I said, right? So suppose your input is this query, right? And now based on this query's yeah, so based on this query's similarity with the key values, you calculate the attention weights. And now based on those attention weights, you will basically do an average, weighted average of the values. Okay. So these are the uh, three most essential things for attention: query, key, and value. Okay. So now self-attention means what? That you are basically, your source of creating this query, key, and value are same. It's not always that they'll be same, but in self-attention they are the same. So they are being created from the same source. Okay. So what happens is, suppose you have an input embedding X, and now what you do is, you want to create these query key and values, and you have to keep their dimensions as well, same as well. So again, your purpose is what? Your purpose is to create that weights, those weights alpha that I showed, that you have to create, right? So now what they have done, what they have shown here is that, um, what you do is, you take this X and you learn a transformation WQ to learn the query vector. Then you learn this, again you take the same input X, you have a different set of parameters, learnable parameters called WK, and you project this X to another vector called K. Third, again you take the same vector X and you have another learnable matrix WV this time, and what you do is, you project this X to some vector V, right? And now in order to, so what is the idea? The idea is that, uh, so self attention is what exactly what I mentioned here, that you basically, these are all similar things, these are all word vectors. So you are basically, all these word vectors are, so whatever similarity computation you are doing based on the neighborhoods, so that is happening among these words only. So they are a unit, they are a sentence. And since they, so because they are part of a sentence, you can think of them as part of one team basically. And now what you are learning is, you are learning a similarity between your current word and the next word. So that is what that is the crux of self attention. So that is being showed here in the matrix notation. So again, as I said, the all important thing is that you learn the alphas, basically the softmax function that I showed, and that is achieved through this particular formulation. So you start with an X. So X is basically nothing but your, suppose you are um, nothing but your embedding vectors. Okay. And so from these embedding vectors, you learn the queries, keys, and values in this way, right? And if you go back, you'll see that, if you compute, so again, referring to the, to the paper of Vaswani, what happens here is that you have to take the query, you have to take the key, and you do I mean, dot product of them, q times k transpose, and do a softmax over that, and multiply that with v. So what did I say some time back, that you have this query, based on this query, and based on the similarity of the query with respect to the keys, you will figure out the attention weights, and based on the attention weights, you'll do the weighted sum on this v, right? So that is what is, that same operation is done here. So you take the query and the key, and compute the uh, alpha values, and do a softmax, so that the summation of those alpha values is 1, and then you multiply them with this v in order to get the weighted sum, and the result that you get is called z. So some sort of example is shown here. So you begin with some, suppose this sentence thinking and machine. right? So they have two embeddings to start with, x1 and x2. So now what you do is using x, so you have this sort of these three learnable parameters, wq, wk and wv. So x1 times wq gives you q1, x1 times x2 times wq gives you q2. Similarly, x1 times wk gives you k1. Similarly, k2, v1 and v2. Using v1 and v2 is generated using by multiplying x1 and x2 with wv respectively, right? And now what you do is, suppose like in one of the examples I was showing you, that there's this dot product attention, where how do you compute the similarity between two vectors? That is just through dot product. So that same thing is shown here. So how do you compute the score? So as I said, what you have to do is your scores have to be computed using your queries and keys. Okay. So you find the dot product between this query and key. So q times k1. Suppose this is some 112. Similarly, q2 times k2 dot product, and suppose this is some 96. Okay, and then this thing is this divided by root over dk is done for some computational ease. I'm not sure why they do this, but yeah, they do this and they show that this is beneficial. So this dk is basically the dimension of the key vector. So suppose if the dimension of the key vector is 64, then root over dk is 8. So that is why you divide this thing by 8, this dot product. So 112 by 8 is 14, 96 by 8 is 12, right? So now you have got the inside of your this softmax. Okay, so this is basically nothing but your scores that you got with respect to x1 and x2. Okay, and now you simply do a softmax over them to get the probability distributions. And now, so now note that just by doing the softmax, what you have done is you have obtained two scores with respect to these two what do you call it? Yeah, these two embeddings that sum up to one. Okay, so now you basically do a softmax. So what I said is that you have to combine the values based on the weights that you found in this particular stage, and that is how you basically combine this softmax with v1. So basically what you do is this v1 into 0.88 and v2 into 0.12, this gives you this z1. Okay, so this is how you basically calculate the weighted average. And this is how basically at the end of this computation what you get is nothing but your this you started with this vector, and now you end up with another vector, which is another representation for the word thinking. Only now your this machine's word, the information of machines has come here. Okay, so similarly you can also calculate the embedding for z2. So because you can see here that this entire calculation is for z1. Why? Because you are using q1 both times, right? So you start with z1 as this first word as the query this time. So if you want to calculate z2, then you have to take the query as q2. So that is more or less self attention. Multi-head attention is nothing but you, instead of, so here what I showed you is that you convert this x to q using some wq matrix. But what if you do not learn just, so this basically kind of, this projection basically, uh, every projection like this basically helps you learn a new relationship between all the words in the sentence. So what they are saying is that instead of learning just one matrix like this, I mean, these are not matrices. This is like a triplet: WQ, WK, and WV. Instead of learning just one triplet, why not learn multiple triplets? Okay, so that is what is happening here. So instead of learning just one W, Q, K, and V, learn 8 such W, Q, K, and V. Okay, so that will give you that many. I mean, so every time you learn a different W, Q, K, and V, that means you are learning a different sort of relationship between among your words, right? So that is what is meant by multi-head attention. So all you need to do is, instead of learning just one matrix, you learn multiple. In other words, in the as given in the paper, you learn 8 heads like this, and the rest of the tasks are very similar. So you basically, for each of these queries, for each of these matrices, you get a separate key query value. For each of these key query values, you get a separate representation, and then you concatenate the resulting Z matrices, and then multiply them with some output weight matrix to get a final representation. So that is how this multi-head attention is achieved. So this is nothing but, instead of doing self-attention once, you do it multiple times and then combine in some sense. Right. So now that we have gone through transformers in a little bit detail, again, encoder, what does the so now we have come to the encoder. What does the encoder do? So you have an input sentence here, and you have a multi-head attention attached to it, right? So what you do is, okay, I think it's given in a little bit better way here. Yeah. So you start with, again, this sentence, thinking machines. So there's a x1 and x2 attached to it. So don't forget that you have to add the positional encoding to these vectors as well, right? So that gives you some, this yellow x1 and x2. Then you perform this self attention, okay, using the multi-head attention concept. So now you basically, the output of attention is always that, for a given input word, you are getting a context rich representation. So you give an older representation, and you always get a new representation for each word. That is always the output of self attention. So this yellow x1 and x2 are given as input. You perform self attention, you get z1 and z2 as output. And now there's some formulation called layer norm. So again, that is out of scope for today. But yeah, some layer norm is there. So what you do is, first of all, obviously, you do not lose this x1 information that was there. So that is why you add this x with z. So whatever, in the matrix notation, whatever x's you had in the beginning, you add them to the z's, so that the x information is not totally lost. And then you do a this operation called layer norm, right? So this layer norm gives you some new, again, a context rich representation of this first and second word in terms of this new z1 and z2, and then you send both of them to a feed forward neural network, and some add and normalize layer is there. So add and normalize is nothing but this, again, this layer norm thing. So basically, in a transformer, you have these layers. One is the multi-head attention, then add and norm. So add and norm is this one, then a feed forward, and then again add and norm, right? So both of these are basically nothing but layer norms, okay? And you repeat this in the original paper. It has been shown that you have to repeat this 6 times, but yeah, obviously there are so many variants of transformers nowadays which use different things. So this is the entirely the original architecture. And now decoder, right? So decoder is actually very similar to the encoder, just that instead of now normal multi-head attention, you have masked multi-head attention. Masked means what? That here, instead of okay, not this one, let's again go to the beginning. Yeah, here, instead of, so normally during attention, what do? We look at all the neighborhood of the current word, right? But when you are decoding means you are generating word one by one. So then you cannot, when you have generated this jth word, you have only looked at the previous 1th word to this j minus 1th word, right? You haven't seen the j plus 1 word yet, right? So that is why you cannot perform attention on these words. These are all future words which have not been, theoretically, by the model, the model hasn't seen them yet, so you cannot perform attention on them. So that is what is called masked attention. So basically, you, all you have to do here is, you perform attention but only on the all the previous neighbors of you, not the next neighbors. The rest is the same. So you can see that the rest of the things are same. Just that obviously one more thing is required here, that first of all you mask all the right side words uh, to your current word, and also you take in the information that you learned in this particular encoder, that also you require for decoding. So the complete architecture is something like this, that the encoder is, so here this is the encoder where you begin with the input embedding and add the positional embedding and do multi-head attention, then add and norm, feed forward, add and norm. This is repeated some n times, and now whatever output you get here, you are sending it here, right? So decoder side, what happens is in the output uh, you have the output embeddings, you add the positional embeddings, make sure that you are not looking at the right side, do an add and norm. So this is basically masked multi-head attention on all the words that are already generated by the model, and then you take in the information from the encoder, again do a multi-head attention, and then uh, do a feed forward, and similarly go, I mean, you have some other parts of the network. So that is how these transformers are. So this looks a bit complicated. So yeah, I mean, it is complicated, but this works remarkably well. And even though this was originally meant for tasks, sequence to sequence tasks like machine translation and uh, suppose question answering and all, so people then later went on to see that not only are these useful in architectures like images and audio and whatnot, they are also very useful when you have two of them or three of them together. So suppose when you are dealing with visual question answering, where you have an image and a question in text, so you have image and text together, or suppose even video where you have image, text and audio together. So for all of them, people have seen that transformers, they always generate state of the art. So these are the most remarkable architectures now, till we get the next architecture probably. So yeah, let's. I know it's a lot of time has passed, but yeah, quick run in the into the code. So the code is actually, I found it, I went through it a little bit and I found that it's actually it's a very well written code. So everything has been explained in great details inside the code. So this entire thing, how the, so diagrammatically they have shown like how you input some, you have a input sentence, hello, I love you. How do you tokenize and embed it? Tokenize means you tokenize the individual words, and then you find the word embeddings for them, the starting word embeddings. You add the positional encoding, and then you begin with your multi-head attention and feed forward layers and so on. So this is your encoder architecture, and so they have also shown here how to compute. You have a four-word sentence here. So X is a matrix of four words, x1, x2, x3 and x4. So this is x1, x2, x3, x4, and you yeah, yeah, so you multiply them with this query key and value matrices to get your query key and values, right? And correct. And now you perform this attention operation. So again, the single most important thing in attention is to figure out the weights, attention weights. And once you have the attention weights through the softmax function, you do a weighted sum on the V's, right? And then you send this information across to the uh, decoder in order to um, generate the sentences one by one. Right. So whatever most of the things that I talked about are shown here. The same diagrams are shown here. So let us go a little bit past them. So okay. Yes, so each component is given here, and the good thing about this code book is that everything is very well defined here. Everything is written very clearly. So suppose each word embedding is of size 512, and our vocab size is 100. So we have a list of 100 words where each word has a dimension of 512, the initial embedding dimension. So our embedding matrix will be of size 100 cross 512. This is understandable. So these matrix will be learnt on training, and during inference each word will be mapped to corresponding 512D vector. Suppose we have batch size of 32 and sequence length of 10. So there are 10 words in your sentence. The output will be 32 cross 10 cross 512. Because you have a batch of 32, you have 10 words per sentence, and your output dimension also is 512. So uh, as I keep saying, the input to a transformer is a list of words. Output to a transformer will also be a list of words, right? So here in this particular section they have defined the word embedding in the way they have said. So there's a vocab size, there's an embedding dimension. So the self.embed consists of some embedding of the size that they have mentioned here, 100 cross 512. Just that this embedding will be learned in the process. So now the next step would be to generate the positional encodings. So as it's written here very well, so you need two things. One is the meaning of the individual word, and also where is the word located in the sentence, right? Otherwise it's difficult to understand. I mean, for the model it will be difficult to process that word if it doesn't have any idea about the position of that word, right? So as I defined some time back, pos refers to the order of the word in the sentence. I refers to the position along the embedding vector dimension, right? So yeah, so here everything is defined. So basically, because we have to do this programmatically, we have to, it's easy to understand everything when you look at it uh, uh, from the vector point of view. Generally I find it easier to look at it from the vector point of view, but when you finally compute everything, everything has to be in matrices. So whatever I described, all you have to do is you have to combine them in form of matrices. So you have the input sentence matrix, which is a collection, which is basically the stack of vectors of the individual words in the sentence. All you have to do is add the position embeddings, which you compute using this formula in terms of a in terms of a matrix. Now you add these two to get your final, starting embeddings, right? And this, how to generate this positional encoding, that code is given here. So you can see this math.sin and math.cos are there. Mm, Making sure that you are using the appropriate formula at your odd and even positions in the vector, right? So then what is self attention? Suppose we have a sentence, dog is crossing the street because it saw the kitchen, right? So what they are trying to say is that, uh, suppose this word it, right? So what does this word it refer to here? I mean, what does this word mean at all? Oops. Yeah. So, like, humans, when they read it, it's very easy to understand that it is being referred to dog. But now see that given this big, huge sentence, it is here, whereas dog starts here. So there's so much distance between these two. So normal RNNs will definitely forget that this it was referring to the dog, or it will be very difficult for them to remember that. So this was not very easy for machines. So now self attention, what it does is it allows to look at positions beyond the previous word or the next word, right? So it can, this it will, if you want to get your contextual attention based vector on this word it has to look at dogs, is, crossing the street, everything, every other word in the sentence it will look at to create its own embeddings, its own embedding. So that is why the self attention thing is important. So right. So how do you do that? The first step in calculating self-attention is to create three vectors from each of the encoder's input vectors. So that is the definition of self-attention, that from the encoder's input vectors only you create all the three key, query and value matrices. So we create a key, query and value matrix for, vector, query vector, key vector and value vector from the encoder's inputs. Okay, and set them to be of dimension 64 like I mentioned in some time before, right? And because we want multi-head attention is what, that you do self attention 8 times with 8 different query, key and values, right? So we'll have 8 different self attention heads right? So that is how it was defined in this 8 value was also defined in the paper in this way. So most of the things that we have talked about are based on the paper of Vaswani et al. So right. So okay, we have a batch size of 32, sequence length 10, embedding dimension 512, and mm, so after the embedding and positional encoding, our output will be of dimension 310 cross 512. Let me increase the size a little bit. Yeah, right. So we are going to resize it to this 32 cross 10 cross 8 cross 16 in order to accommodate the 8 heads because it's the number of heads, right? And now what we would want is for our we want this in the output. So leave the batch size for now, leave the sequence length for now. We need 8 quiz, 8 queries and 8 values. That is why this 8 cross 64 is there. Okay. Now, so these here you'll see in the steps 2, 3 and 4 all the values are sorry, all the steps are given very neatly in calculating the key query and value matrices first of all, and then also computing the individual scores, right? So first you calculate the so you first calculate the score. So we'll multiply query matrix with key matrix in this form qk transpose that I showed in the slides, and then you divide the output with the square root of dimension of key matrix and then apply softmax over it, right? And then this gets in step 4, this gets multiplied with the value matrix, right? And this is by the rule of multi-head attention. You pass this through a linear layer and to form the output of multi-head attention, right? So that piece of code is defined here. So on your time, go through it. If you have any doubt about the theory that we have taught this week, this part of the code will make it easier. So this is basically how you calculate the query keys and values, and you do it 8 times also. You do it 8 times separately. You generate query key and values for uh, you know 8 times, and then you do a weighted average as we talked about. So you can see all the functions are here. You do a softmax, and then you do a matmul with the scores and the scores that you get here and the v vectors. Right.
Ma'am, can you share the
Yeah,
URL in chat box?
I'll just do it. Yeah,
Thank you, ma'am.
yeah, sure. So now they have nothing. The next part is basically they have defined the encoder here with your input embedding. So the exact thing that I described, that it will start with the input embedding, it will add the positional encoding, do multi-head attention as described above, then this add and norm. So this layered norm thing that I mentioned about, so PyTorch already has an implementation for that, so you do not need to worry about it. So you do the add and norm, then you do a feed forward, and then you do another add and norm. So that will be your final encoder, and obviously you need to repeat this this pair for some n number of times. So correct. So let's pass through these a little bit, but yeah, this is going to be your transformer block. So transformer block. So some yeah. So you first of all you have this multi-head attention. Then you have two layer norms. So if you remember, there's a feed forward network. So there's a layer norm on top of this multi-head attention, and there's a layer norm on top of this feed forward. So all of these are defined here just like expected, just like the diagram. So I think when you go through it, you will find it very easy to understand because everything is correlated with the diagrams given. So it's actually very easy to figure out what's going on. So you have the key query and value. You find the attention from there in here. Then you add these two as in you do not lose the input. So that is why you add this attention out with this particular value, so that this is a kind of like a residual connection. and then you basically do a layer norm on top of that, right? And similarly you have this feed forward. You do the same thing. You add the this output of the first part. So output of the first part means this one. So this one again, see, you are going to add it back to the feed forward layer. So that is what they have done. So this norm1 out was the output of the first part. You add it with the feed forward output and you get the residual connection, and then you apply the second norm layer, layer norm layer. And so that becomes, so this is your transformer block. And a transformer encoder is nothing but you are just repeating this for some number of layers. So that is what is done here. And similarly now decoder is there. So decoder has a similar architecture, just that there's a masked multi-head attention here. So what they say here is that yeah, so this masked multi-head attention is basically called the decoder attention, because here you are doing attention on just the decoder words, the previously generated decoder words. And there is, so it's written here actually, where did it go? One is the decoder attention and one is the encoder decoder attention. So encoder decoder attention is what? This is where you combine the encoder information that is coming here in this arrow. You combine it with whatever decoder information, whatever information you got from here basically. So that you have the you need the encoder information to basically do your decoding step. So that is this is how you are getting the encoder information inside your decoder network, right? So mask is what? Mask is used because while creating attention for target words, we do not need a word to look into the future words to check the dependency. So that is exactly what I say, that as at a single time point when you are generating a word, you do not know what your future words are. So that is why you cannot have attention on those words. You only can look at your previous words. So that is why some mask is required, which means that at every position, this is this if this is your so this sort of a matrix is created. This means what? That when you are the first word, you cannot look at the next 5 words. Okay, next any number of words. When you are the second word, you can look at yourself and you can look at the previous word, but not the third, fourth, and fifth word. Similarly, when you are the third word, you can look at yourself, second word, first word, but not the later two. So you have a mask like this. So whenever you, suppose if you are at a position I, where suppose I equal to 3, then mask, what does mask do? You create a vector of ones and zeros like this, where all the words to your right will be marked as zeros and all the words to your left and yourself will be marked as 1. So this will tell the model that okay, you can do attention on your previous words and yourself, but not the next words. So that is what is given by mask. And yeah, I mean the rest of the things are same, more or less similar, just that you need this what do you call it, during the encoder decoder attention, you need the output from the encoder. So as it said here, for this multi-head attention we create key and value vectors from the encoder output, right? So another little bit of code is there. So yeah, so you have a multi-head attention, you have this layer norm, you have a dropout, and you have the transformer block. Because transformer block is like, if you look at the image, this part is entirely transformer block, right? So here first you, this is the, so okay, so this is the decoder block, right? So you what you do is you begin with an attention, again where all inputs are same, but you have to give the mask here, right? And then you pass it on to the transformer block in terms of the key, query, and value. And yeah, and now you have the transformer decoder, where basically you do nothing but this decoder block only you'll have to repeat for multiple times. So that is what is done here, right? We'll also run this one. And finally in a class called transformer they have put everything together so that it can perform everything. You if you want, I mean, decode, encode, and all other things are put here. So there's a self dot encoder, there's a self dot decoder, which does everything. So the encoder encodes, the decoder decodes, and yeah. So simply what they have done is they have created a some source and target, and they have initialized the model here. And finally, one thing that I wanted to mention is okay, so they haven't really run the transformers here. They haven't really trained the transformers here, but yeah, they have shown how to write the code for it. So all of these things you'll mostly get codes, ready-made codes in PyTorch. But yeah, they basically wanted you to look at, have a feel at the because looking at these diagrams, it's very difficult to understand what's going on inside. So this piece of code will actually give you a very good idea of what the individual parts of the model are. So if you look at this summary, you'll see that, yeah, so very clearly you'll see that there's this decoder, and on top of that there's this encode. These parts are basically the encoder parts, and how basically this architecture is constructed. So that is what this code base is about. So yeah, let's call it a day today. But yeah, this is actually a difficult thing, but one of the very most seminal works are this is one of the most seminal works that has happened in our times in front of our very own eyes. So yeah, go through it, and yeah, it will take some time to digest this one, because while I find attention to be easy, but transformers, when you combine all of those things, multi-head attention, self-attention, feed forward, everything become jumbles up a lot. So go through this slowly, more or less in the slides. I mean, it's explained quite well. Go through these examples, that will make things clearer for you, particularly this one. So they'll make it clearer for you. Watch some blogs and all. So that also will help a lot. And yeah, go through this code. So whatever doubts you will have after going through this, I think that will be solved by the code. Fine, let's call it a day then. Bye.
Okay. Thank
Your voice is breaking. Hello? Okay then. So let's leave the call then. Bye.